Welcome to a groundbreaking online event proudly hosted by the Geohazards Community Facebook group in collaboration with GeoLearn Hub Facebook page. As we embark on this extraordinary journey, let's explore together the essence of these communities. The Geohazards Community Group, a dedicated space for geohazards enthusiasts, delves deep into the intricate world of nature phenomena, from the raw power of earthquakes and volcanoes to the erosive forces of nature. From devastating floods to dramatic landslides, our group is a platform where professionals, researchers, students, and enthusiasts converge to understand this phenomenon through structural geology and tectonics, unraveling the secrets of our planet's dynamic nature. Now, GeoLearn Hub page, our esteemed partner, is your gateway to a world of geoscience knowledge. They provide invaluable support to postgraduate students, offering guidance in software like ArcGIS and Global Mapper, publishing papers, and conducting both paid workshops and free content sessions. Their mission is to facilitate learning, research, and collaborating in the geoscience field. Now let's turn our focus back to the event. Allow me to introduce our esteemed moderator, the geologist Mr. Said Maush. He will kickstart the program, setting the stage for the presentation by one of the foremost experts in the field, Professor. He is also a founder member of the Algerian Academy of Sciences and Technologies. His knowledge is unparalleled, and today we have the rare privilege of learning directly from him. In this webinar, we will explore the geologic background of the High Atlas seismic zone, gaining a deeper understanding of the 2023 Adasal earthquake. Furthermore, you'll have the unique opportunity to engage in a live Q&A session where your burning questions will find answers. Thank you for your interest. We invite you to be part of the Geohazards community and follow GeoLearn Hub for more enriching content that we are actually broadcasting via Facebook. Help us to connect with a wider audience by following us today. Let's make our geoscience journey even more impactful.
Mustapha, it's okay?
It's okay.
So, good morning, ladies and gentlemen. Thank you for being here. And I think that before Mustapha lecture, I would like to give a brief overview of his work and provide a few miles for those who do not know him. So, Mustapha is a professor, senior research in the EOS University of Strasbourg, and he worked on active tectonic. So before moving to Strasbourg, Mustapha was a senior researcher at CRAG in Algeria, no? And also in several laboratories in Europe. One can say, for example, Orsay University, Royal University in Belgium, and INGU in Roma. Mustapha is a member of an active deformation team at the Institut Terre et Environnement de Strasbourg, and develops programs in the study of earthquakes faulting, seismotectonic, paleoseismology, paleotsunami, and geological hazard. He has played a significant role in the identification of earthquake faulting in the interplate and interplate tectonic domain. Mustapha teaches active tectonics and paleoseismology and supervises more than 15 PhD theses. He has been also coordinator and PI in previous and current scientific projects in Europe, Northern Africa, and Middle East. We can say maybe some projects like PaleoSys, SAFE, Relief, Transfer, FP7, etc. And in Africa, Mustapha is a coordinator of the UNESCO IGCP projects entitled Seismic Hazard in Africa, particularly the seismotectonic map of Africa. In Algeria, Mustapha has been also coordinator and PI of several projects like PNU, ACI, and CMEP project. Mustapha is author and co-author of more than 100 peer-reviewed scientific publications in international journals, with more than 8,000 citations and each index of 56 in Easy Web of Science. Mustapha was also freeman of the city of Shilif in 1980 during the El Asnam earthquake. He is elected president of the African Seismology Commission in 2018, I think. Mustapha is also honors medalist of Aristoteles University, Thessaloniki in Greece. He is also medalist of the Italian Ministry of Interior. He's medalist of the Turkish Geological Society and honor medalist also of the Belgian Luxembourg Geological Society. Professor Mustapha Meghraoui is founding member of the Algerian Academy of Science and Technology. So before I give the floor to Professor Mustapha, I would like to say on behalf of our geohazard community, thank you for what you are doing and good luck for the future. I ask all participants to turn off their microphone and camera, and at the end of the conference, around 20 minutes debate will be opened. You can also post your question on the site. Maybe I remember to the participant that the certificate of participant to this webinar is available, and participants who want it can fill out the document on the website and send email. Thank you. You are welcome, and I give floor to Mustapha. Mustapha, you are welcome.
Thank you, Said. Do you hear me?
Yes, it's okay.
Okay. Thank you, Said. It's a pleasure to be here, and I would like to thank all the members of the geohazard community, and specifically those who are directing the geohazard for this invitation. The occasion is quite sad because you asked me to give a talk and presentation right after the 8th September 2023 Adasila earthquake of magnitude 6.8. It was less than 10 days ago, and the damage was so large, so big. Then the fatalities is reaching now more than 3,000, and a large damage in the area of the High Atlas in Morocco. And so I take the opportunity to send our solidarity to our Moroccan people, our brothers from Morocco, and our condolences for the victims. The earthquake took place right in the High Atlas. The term High Atlas, the name High Atlas is because those mountain chains in the Maghreb are the highest mountain chains, and they reach like the Jebel Toubkal. They reach more than 4,000 meter high. So the earthquake took place in that situation. So I'm going to make a report on the earthquake and give some of the first results that have been obtained recently from that earthquake. So in the last 10 days or so. So I don't know what's happening. Yes, okay. So first of all, I would like to show you these pictures here about the damage, the severity of the damage. The items here, the pictures, and also the damage distribution are done by the United Nations UNITAR, and this is a courtesy from my former students and student and colleague Samir Belabbes, who is working in Geneva. So the earthquake took place at 10:11 universal time. And you know, the people, it's we have to count universal time +1, because it was 11 local time, and maybe some people were already sleepy and they were all in their houses. So this shows or may explain the large number of fatalities during that earthquake. The damage distribution you see here, the damage distribution is quite extensive in the high Atlas, and the main shock was so damaging that the intensity reached 10 to 11 MMI. This is what is done by our colleagues from the UNITAR, United Nations institution. Now here, the number of fatalities is increasing. Now we are reaching 3,000 and maybe more, because some of the villages have not been investigated yet. The two images here, you have the Pleiad are the Pleiad images. The Pleiad are high resolution images from the National Center of Space Agency in France. And you see here the image to the left is before. The image to the right is after, and you see a whole quarter here totally damaged. Some others also, some other houses here also damaged. Some other houses. So you see that the severity right from the images when you are in the field for the investigation in the ground. It should be higher, because some houses, they seem standing up, but in reality they are totally damaged. So this is the distribution of the. I have to note something that maybe many people, many journalists also, they mention about Marrakesh. Marrakesh is here. Marrakesh is about 80 kilometers away from the epicenter. So this is something that we have to take in mind. Sorry. Here are the damage. You see some houses are partly damaged here, for instance. Some others are totally on the ground, totally devastated. There has been a problem with the landslides and block falling, such as the local people needed a bulldozer to free the roads and the paths. And you see but the problem is that each region, each village didn't have a bulldozer to be able to let the people from the civil protection to have access to these villages. So these villages went isolated. Became isolated for several days, and even you see that the constructions are mainly done with adobe and mortar, simple mortar with clay, but even the construction with concrete, they were severely damaged. So this is the situation in the High Atlas. And until now, some of the villages have not received enough help to help the people, and also to count the victims. Now let's go to the topic. This is a map of the seismotectonic of the Maghreb region. And you see, apart from the plate boundary, you see seismicity is very, very dense along the plate boundaries, and from the Gloria here, toward the Gibraltar Strait, the north of Morocco here, with the Rif Mountains, and then along the Tel Atlas Mountain in Algeria and Tunisia. So you have a large number of earthquakes, and the largest one is the Al Aslam earthquake that took place in 1980, magnitude 7.1. But if you go inside the continent and here in the African plate, you see that there is a large fault zone or Sutter zone, named the South Atlas Sutter zone here, and this South Atlas zone separates the African platform from the Atlas Mountain to the north. So there's not much seismicity along this South Atlas Sutter zone, but there is seismicity. We cannot exclude that there is seismicity. The problem is how much frequent and how large. So this is what we are going to investigate. Just for the record, this is the Agadir earthquake here, and in southern Morocco, and this is the area of El Hoceima, who was active and damaging also in 2004 with the magnitude 6.4 in 2004. So this is the introduction. I'm going to concentrate then here in the High Atlas Mountain, where the earthquake took place recently. Another results that we can see is the at what rate the active deformation is acting in the Maghreb region, and for the new data, the new results that we obtained recently, either here in Tunisia, but okay, yes, okay, I understood. So in Tunisia, in Algeria, and also in Morocco, so there's a large number of GPS data, GPS measurements, and including also in the Sahara here, where we can measure the active deformation, especially between the African platform and the Atlas Mountains of the Maghreb. You see here the list of the colleagues that contributed to these measurements. Especially here in Morocco, there's the work of Koulali and others in 2011. They have measured the nice network here across the Atlas Mountains, across the Rif and the Atlas Mountains, the Middle Atlas and the High Atlas, and it shows the rate of active deformation. It shows, we can see, for example, from this point, who is in anti-Atlas, and this one is the High Atlas, you can see that there is not much active deformation. It's not very fast. It's very low. It's less than 1 millimeter per year. This is the same here from this station and this station here in Algeria, and it's the same from this station here in other stations here in Tunisia. So along the Sutter zone, the active deformation is quite low. Now, if I continue and concentrate on Morocco here, we have all the seismicity here between 1950 and 2012, and you see that most of the seismicity is along the plate boundary here in northern Morocco. When you go further south, there is still a seismicity. It is moderately dense, but it exists. It exists along the South Atlas Sutter zone here, and again here I show the Agadir. When you see here the GPS, as I said, the difference between the velocities here is very small. You have a little bit more velocity, for example, at this point with regard to this point, or this point with regard to this point, and it is when you see here the just a minute. Sorry. Yeah. Okay. You see here the scale. It is in any way less than 1 millimeter per year. So it's a very low rate of deformation. If I continue here, I have to remember. We have to remember that that region experienced a very large earthquake, large and damaging earthquake on 29 February 1960 earthquake. It's a 5.9 earthquake MS, and you see that the city of Agadir was severely destroyed, and the fatalities was very high. Some they say 4,000, some other they say 12,000. So it's in any case it was a catastrophe in 1960. So this has to be counted for the activity along the South Atlas. Some investigations has been made previously. You see here the city of Agadir, and what was our interest? It was that wanted to investigate the rate of uplift of activity in terms of uplift rate. Looking at the marine terraces, you see here with the arrows, we see here a marine terrace in conformably lying on folded unit, and indeed here to the right you have a large area here with the folded units here, your folded geological units, and next to the Sousse basin. So this is not only you have a topographic offset here, but you have also some faulting, we call them flexural slip faulting, along the Atlas, the South Atlas front. So this is really the South Atlas front. You see here all these terraces uplifted, and the uplift rate here is 0.1 to 0.3 millimeter per year, according to the dated marine terraces that are here. So this is what we're obtaining. So why is it important? It's important because we want to understand why the earthquake they take place in this region, and we are going to compare with the region of Adasir earthquake right away. So if I continue, what we did, the investigation that has been done, looking at the epicenter in that region, and this is the damage distribution done by Roté, who is a seismologist from France. So at that time, he did a detailed investigation. You see here, the damage reached the intensity 10 in MKS. So it was really damaging earthquake, although it was only 5.9 and reached MKS 10. We think that the hypocenter was shallow, less than 8 kilometers, due to the large damage area, but not at large as the Adasir earthquake, the recent Adasir earthquake. What has been done also, we did some Okada modeling here just to see how the active folding correlate with the geological structure and with the folding, and you see, consider that the fault is blind, didn't reach really the surface. You see here the cross section that shows you the active deformation at the surface, and also here a focal mechanism that can be taken from that earthquake. So this is what was done before the Adasir earthquake, actually. Now, if we go to the Adasir earthquake, you see this is the Agadir, and the Adasir earthquake is right here. You see that this is from the modeling, it's a truss fault. This is also the truss fault. We favor the northwest dipping, high angle northwest dipping faulting, is almost east northeast, west southwest, and on the background here I put just the decorrelated INSAR results that I show here to the right. You see here that there is INSAR results obtained by a group of Lixar Comet in Leeds University. So you see here quite clearly here number of fringes, quite, let's say, with circular shape on this block. And another group of fringes here, also like an elliptic shape. This one is the area that is going away from the satellite, and this is going close to the satellite. So this shows clearly that you have a northeast, south-southwest rupture at depth, probably responsible of the surface deformation. This is Sentinel-1A in descending orbit, with two images from the 13 August and 11 September. So what is interesting here is to show that this is right inside the high Atlas in the mountain. In terms of historical earthquakes, there has been a historical earthquake in 1719 near Marrakesh, but probably the source, the seismic source, was in the high Atlas. And here Agadir was destroyed also by an earthquake in 1783. So it means that this area was under pressure and under stress, continuous stress, and generated earthquakes in the past. How large were those earthquakes? We don't know. We did more investigation in, for example, in paleoseismology and active faulting in the area. The rupture that we could infer are here put in dashed, because we think that the rupture did not reach the surface, simply because I didn't say it before, but the earthquake was is put as 18 kilometer, about 18 kilometer depth, so it's quite deep. And when we see the seismic moment here given by the W phase moment tensor from the USGS, we have here 2.3 10 to 19 Newton meter. It means that if you take a rupture of about 30 to 40 kilometers and 18 kilometers depth, so it is quite likely that the rupture did not reach the surface in the area. No, we have to know that the area is very mountainous, and you have valleys and with plenty of landslides, and so it would be very difficult to see if there is surface faulting, unless you have escarpment with a large escarpment with a large vertical movement, like 2 meter or 3 meters, which is really unlikely in the area. So one thing that I wanted to say previously is that the distance between the Adasir earthquake and the Agadir earthquake is about 100 kilometers, and this is shows that. And go to the question: is there any relationship between the 1960 here and the 2023 here? We have to note that the distance is not in favor of putting a relationship or maybe going to a modeling of a stress transfer between the two earthquakes. So we have to think on another process in the area. Going to the INSAR, INSAR was actually very important because it shows where the earthquake took place. If you see, for instance, the epicentral location given by the different institutions and research centers around the world, there are many locations. They have, let's say, plus minus 5 kilometer uncertainty, and those uncertainties let us a little bit asking where the earthquake took place really, and how we could correlate what happened at depth along a fault rupture and what's happening at the surface. So only INSAR shows the correlation, is able to make a correlation between what's happening at the surface and what's happening at depth. And as I said here, so the fringes here, they show quite a clear region of uplift, and next to it you have a clear region here of downthrown, of kind of a subsidence here with these fringes around here. So we could trace a fault northeast, east-northeast, west-southwest trending fault, and also the distance can be around 30 to 40 kilometers. This is the correlated, and you see here the region of maximum displacement at the surface, and uplifts, and also downround. And you can trace here the separation between the two. It doesn't mean that the rupture reaches the surface. This shows that the rupture didn't reach the surface at this point here. So these are results obtained immediately after the earthquake. The earthquake took place on late night, 9 September in the morning, and the second image he acquired on the 11th of September allowed to have this interferogram. Now other interferograms are calculated to obtain maybe a better image of the surface deformation. Other institutions like the INGV in Rome, but also the USGS, they did some modeling on the fault size. Here you have the fault size, and also here you have the strain distribution. You have here the rupture with the slip distribution. It shows that we have quite a simple rupture with a simple slip distribution at depth. You see the depth that from the inversion of the surface waves reaches something between 15 and 35 kilometers. So curiously the rupture itself is quite deep. It's quite deep in this area. So now we wait for the local stations. What they will tell us about this depth of earthquakes during the Adasil earthquake sequence. Now, if I speculate a little bit and put here the epicenter, the focal mechanism here with the thrust fault, and I said we favor the east-northeast, west-southwest faulting with the dip around 70 to 69, 70 degrees, and put here how we can project the fault rupture here in dashed, because not visible at the surface. You see, you have some morphology here that looks like they adapt to the fault zone here, to the infrared fault zone. But in any case, the fault is blind, and it's blind in this way here. That this is a modeling done by Stein and King in the past, when right after the El Aslam earthquake, and you saw how blind the fault can be. It can be at 1 kilometer depth, 2 kilometer depth, maybe more. But you have always a signal at the surface in terms of a folding, uplift, and downround subsiding block. So this is what we can say about the active deformation. Here it's the same situation as for the blind fault here, with an example from the Coalinga earthquake in California, and this is the El Aslam earthquake with the surface faulting. You see with the surface faulting, the fault reaches the surface and shows really a clear deformation with uplift and downround. And but this is not the case we are in this situation with a blind faulting, blind deformation, confirmed by the INSAR. So this is what we can say. So we can continue here. I can continue and describe in the description. I plot here all the aftershocks from the Euro-Mediterranean Seismological Center, which collect the data from the different seismological center in the area, from seismological center in Rabat, and also in Algiers and in Spain. And So we can say that this distribution here is reliable on the 8 September earthquake. You see that the distribution is right next to the epicenter here, and we can say that this aftershock activity is continuing until now, and we have a lot of magnitude 3. The main aftershock is curiously low. We have low magnitude, it's 4.9. So for a 6.8, it's quite low. I remember, if I compare with the Zemmouri Boumerdès earthquake, it was also an MW 6.8, where the largest aftershock reaches 5.5. So it's a little bit different situation here. But you see here the distribution of all the aftershocks, and it is quite close to the main shock, here. To the right here, it's a CFF of Coulomb failure function that shows maybe a possibility of a stress transfer in this area. This is done by Igor Takarish, my ex-student. He's now in University of Algiers, and he was kind enough to pass me this modeling. And we see here clearly the zone of loading zone along the rupture here in red, that reaches 2 bars, and the zone here that is with unloading zone here in the middle of the rupture zone. How much this loading here area during the earthquake and after the earthquake will affect the neighboring faulting, we don't know, and we are going to follow the situation, and it is not excluded that another earthquake may take place, especially because the main aftershock 4.9 is quite low in this area. So this is what we can say. Now, how do we understand the origin of this earthquake? There is a very nice paper just recently published by Lanari and others in 2022 on the High Atlas, and what the conclusion, looking at the geology of the region. When I say the geology, really the background geology from the substratum to the recent activity, what they say that probably the one of the explanation that one may have about the high topography of the Atlas mountain in that region is due to the mantle activity that crosses go up and crosses the lithosphere and transfer the active deformation and the uplift to the surface. So this is something that is modeled. It is a model looking at the density in the mantle and the lithosphere, and also modeling the velocity and magnitude in this area in terms of active deformation as well. So this is one of the explanation that I also agree with this. Otherwise, how can we explain the occurrence of these earthquakes and the high magnitude, high magnitude 6.8, and also the high topography in this area? I repeat again, the highest topography is the Mount Toubkal, and it is 4,100 meters in the High Atlas, and is immediately east of the main shock. Another work done by our colleagues from Morocco and Youssef Timurelli, who did the seismic tomography on the area, and you see here it is crossing right the Atlas Mountains and also the anti-Atlas, but it is crossing the Sus Valley here and also the High Atlas, and you see that in this study with this looking at the structures, you see clearly here a thrust fault here. And what is red means that there is much more activity and much more seismicity, and what is blue is less activity. And you see that the separation here shows clearly a thrust fault that is a thrust fault corresponding to the South Atlas Suture zone. And so this shows that at depth, the way that the lithosphere and is organized, it is organized as a function of what we see at the surface in terms of topography. So this is published in 2015, so long before the earthquake of 2023. As a conclusion, what I would like to say, just a number of points here, which is the Adasil earthquake occurred in high Atlas magnitude 6.8. So we know this. And the moment shows us that the rupture, the fault rupture, the earthquake fault rupture may reach 40 kilometers. It is east-northeast, trending reverse fault, and dipping 70 degrees to the north-northwest. So this is what we can say for the rupture dimension. It is a branch of the South Atlas Suture zone. It means that the South Atlas Suture zone is active and can be active all along, not only in Morocco but also in Algeria and Tunisia. And we can remember, for example, in the city of Biskra, there was an earthquake in 1867, I think. I don't remember exactly the date, and it was a damaging earthquake at that time. Then this area of the South Atlas and the Atlas in general, and also the Maghrebi, the general, it's a region of transpression. Transpression means that you have at the same time lateral movement on fault. It's faulting, east-west trending faulting with the right lateral movement, and you have at the same time convergence or contraction from north to south or north-northwest to south-southeast. So this shortening rate, if I compare with the GPS, it says between 0.5 and 1 millimeter per year. And the uplift rate is between 0.1 and 0.3 millimeter per year. Millimeter per year. So you see here the percentage between the shortening rate and the uplift rate in the area. Then one observation that I can make, which is maybe speculative, but let us do it. The famous mosque named El Koutoubia in Marrakesh was not damaged through the centuries, and but it was damaged during the 8th September 2023 earthquake. I think the not totally damaged, but quite moderately damaged. The summit of the minaret was shaken and was affected by the earthquake. So this mosque, this minaret, exists since it was constructed in 1158. So it means that during all these periods, this mosque didn't experience any damage. So it means that in this area, perhaps the return period of large earthquake or damaging earthquake is more than 865 years, if I come to the construction of the El Koutoubia. And this correlates with the rate of activity. I mean, if the uplift rate or the shortening rate is on the less than a millimeter per year, so it means that the earthquakes are not very frequent. The large earthquakes are not very frequent in this area. So from the seismic hazard point of view, this is an observation that shows that those villages they were damaged since no earthquake took place in the last 800 years or so. So it was difficult to make any plan for the seismic hazard and mitigate the occurrence of earthquakes in the high Atlas. So this is what I can say. This is, as I said, this is like a report on the earthquake of 10 days ago, and I think some other works will be continued on this earthquake in the near future. Just for the beauty of the area here, this is the Mount Tubkal, 4,000 meter, and this is the Ilil village, totally destroyed also during the earthquake. So this is a photograph taken before the earthquake, and you see what kind of topography and landscape exist in this area. That's the end of my presentation, and thank you very much.